All right. Good afternoon, ladies and gentlemen. First of all, I must thank you. Um, Thank you very much for joining in to our fiber focus webinar series. Now, Institute of Technology, University of Moratuwa, um, Division of Textiles and Clothing is trying to initiate this program, trying to disseminate knowledge, especially in the areas of textiles and clothing. And we are trying to sort of reach out to the textile community. I think in that respect, we have initiated this program, this webinar series. We call it Fibers Focus. Now, this is the second webinar that we are conducting under this program. And today we are going to talk about a very interesting topic. This is going to be on moisture management. So before that, I would like to invite all of you, if you haven't already registered to Fiber Focus webinar series, so you can do that. So what I will do is I will share a link through the chat. So if you haven't already registered to our newsletter, you can do that. So by doing that, you will receive, if there are any upcoming webinars that are on this particular or any other topics related to textiles, you will be able to know. And also, this will be a great way of connecting with the other community members as well, which we are trying to do in future sessions. So I will share that in the common chat, so you can go through that link and register. So without further ado, let me introduce the speaker today. And today we have a special personality conducting this webinar. Her name is Dr. Nadika Tisera. She's a respected academic and also an accomplished material researcher in this domain, especially in textile materials and advanced materials and nanotechnology. She's also a senior lecturer attached to Institute of Technology, University of Moratuwa, and she holds visiting positions at many other well-known universities. Her main expertise is on material technology, especially advanced materials and nanotechnology, and she has made significant contributions in this particular field, especially on if you take the moisture management related technologies. She has multiple patents and some already commercialized innovations as well. So I think so she's a very good personality to talk about this particular area. So this is how we're going to conduct this session. So approximately the whole session will be around, there will be a lecture, a webinar lecture done by Dr. Nadika. But after that, so we can have a interactive session where you can ask certain questions in related subject areas, and we can have a small discussion before we wrapping up. So therefore, with that, then I would like to invite Dr. Nadika. And also we are recording this lecture, and the recorded lecture will be shared with you through the newsletter as well. It's also, I think, therefore it's important. If you haven't registered already for the newsletter, please do so. Okay, so without further ado, let me invite Dr. Nadika to deliver the webinar. Thank you.
Yeah, thank you, Dr. Ruchira. So good evening to you all, ladies and gentlemen. So I'm Dr. Nadika here. Yes, our main effort through this webinar series is to transfer some of the knowledge that we have specifically in the textile area and with the industry as well as the community, because we think by sharing the knowledge with you all, we can basically look into these advanced technologies, and also we can look into some new development in textile, because textile industry is one of the biggest industries in Sri Lanka. But in some part, we still lack technological development. So let me share my screen with you. Yes, I suppose everyone can see the screen. If you can't see the screen, please let me know. And also during this discussion session, I would rather say this is not a lecture, this is a discussion session. So you all can raise your hand and you all can share your knowledge, because I know there are lots of expertise in the textile industry, which I can see from the participant list, which you have some of the knowledge as well as the experience also. Right. Okay. So the today's topic is advanced technologies in textile moisture management. Moisture and management. Why do we need to manage the moisture? It's very, very important. Because these days it's in Sri Lanka, it's heavily raining. And few weeks back, it was very uncomfortable and a very dry situation. The heat radiation is very high. So we are facing different climate changes. But we as uh, human, we need to adjust in the sense we need to feel comfortable. So therefore technically people have looked at a certain model called comfortable model called thermophysiological model. So you are looking at a circle, but this circle is very important. Why is this very important? Because we always look for comfortability. Now, from the prehistorical era, people start wearing clothes just to cover them, just to protect themselves. And then it became a fashionable item. And now it is more or less towards certain technical aspect of it. We talk about smart textiles. We talk about high performance textile. We talk about advanced textile. We talk about intelligent textiles. So all of these matters at the cost where we provide a comfortable level of clothing to the wearer. It could be a technical textile, it could be a day-to-day wear, it could be an active wear. So this thermophysiological comfort model is important. In here, I'm referring this as a model. Why model? Because certain theoretical or computational aspect can be incorporated into this one, and then you can develop certain equations. You can develop a computational model which basically looks at your body activity level and the comfortable level that you need, and then it will decide this is the level of fabric that you need to develop. It will look not only to your body activity level, but also it will look into the ambient condition. It is because your activity level, ambient condition, as well as the microclimate and the clothing properties are interrelated. So if you clearly look at this circle, in my inner circle, I have included activity level. It is because this activity level basically decide the physiological characteristics. Thermal regulation is necessary. Why do humans sweat? Humans sweat because it is the natural way of body heat management. Body heat, if it is not managed properly, you will feel uncomfortable. Body heat management is done naturally through sweating. If you evaporate your sweat, once you sweat, you will feel comfortable. If you don't sweat, if your sweat does not get evaporated, you don't feel comfortable. So that is the natural mechanism of body heat management. And then why the microclimate, and what do you mean by the microclimate? This microclimate is very important. These days, the climate of the atmosphere is changing dramatically. We are having a long, like El Nino situation. If it is the dry season, too harsh dry season. And if it is the rainy season, too harsh rainy season. So we call this as a El Nino. It's something to do with the macroclimate. But in here, we are looking at the microclimate. When it's come to the textile, microclimate is very, very important. Microclimate of a textile basically refers to the area between your skin and your textile. When you wear a skin, there's an area or a gap between your textile material and your skin. That area is very, very important when you talk about the comfortable level or the comfortability to the wearer. And then there's another circle, which is my third circle, which are the clothing properties. So for this comfortability, the microclimate as well as the clothing properties are important. It is because the microclimate is managed by your physiological characteristic as well as your clothing properties. The clothing properties includes, it encompasses many parameters. So in here I have given few of them as moisture wicking, moisture transfer, drying rate, heat transfer. So these are some of the basic components or basic clothing properties which directly contributes towards the moisture management or for the comfortability of the wearer. And then these clothing properties are directly related with the ambient condition or the macroclimate. Because the macroclimate we cannot decide it because it's naturally decided. What's the temperature? What is the heat radiation at that moment? What is the wind speed? What is the relative humidity? All those factors matters, and we don't have any control over it as long as we are inside a comfortable air conditioned room. But that does not happen at always. We need to go out, we do body activities, we go to gym, we do certain sports. So therefore, we cannot control the macroclimate. So therefore, what we can do is, we are trying to manage the microclimate. Even the thermal regulation inside your body, we cannot control it because it is a natural mechanism. So what we can do is, we can engineer, we can tailor-make the clothing properties in order to best match the ambient condition and the physiological characteristic of a human body, so then it will give more comfortability. So this model is very, very important. This model is the basic that people look at when they develop highly performance textiles for moisture management properties. So with that, I will look into these moisture management in more technical. It is because people think textiles are more dumb materials. But now it has proven we can do smart textiles. We can develop textile which respond to certain stimuli. What is to do with the smart textile with the moisture management? It is because we can develop textile which basically do changes in their micro areas where it will allow more moisture evaporation. So likewise, we can engineer these management, engineer these textiles. So therefore, in definition, moisture management refers to engineering of the material. Engineering means you make it according to your need, you engineer them, and then different structures you can have, and then you can apply different finishes to control the moisture flow through the textile. It is because when it's come to the moisture management means you have the moisture in here. The moisture refers to the sweat and the moisture that comes to the textile in contact from the external environment. So why moisture? It is because we talk about the water as the moisture. If you take our sweat, it composed of more than 99% the water. The others could be certain salts inside the sweat. So therefore, we need to basically manage water molecules. We need to manage water molecules through droplets or through small evaporated small particles. So that is how you basically manage the moisture. Why? Why moisture management is important? It is because, of course, it enhances the comfortability, it enhances the performance. If it enhances the comfortability, it enhances the performance of the wearer as well as it enhances the performance of the fabric. Sometimes there are certain fabric, if the sweat get absorbed, accumulated over a certain time duration, it will basically gives you absurd level of performance. And also the durability for the durability of the textile product also, this moisture management is very, very important. So when you look at the moisture management in textile, we are basically looking at three aspects. That is fabric structure and the breathability, moisture absorption capacity, as well as the moisture transportation mechanism. So the moisture management is basically controlled through these three aspects. The first one, fabric structure as well as the breathability, and the moisture absorption capacity is also important, and then the moisture transportation mechanism. So if you have a look at these three terms, if you are working in the textile industry or if you have a certain level of awareness about the textile, in technical terms, fabric structure and breathability basically look at evaporation. It looks at absorption and adsorption. And the moisture absorption capacity is very, very important because it decides the comfortability to the wearer. Say, for an example, if you wear a cotton fabric and if it is a cool climate condition, so if it absorbs more moisture, it will feel very uncomfortable to the wearer because once the water molecules get into the fabric, it conducts heats. If it start conducting heat, your body will feel very uncomfortable and chilly. So that is why moisture absorption capacity is a crucial aspect when it's come to the moisture management because you need to manage the moisture to make you feel comfortable. And then the third most important aspect, it is the moisture transportation mechanism. There are different moisture transportation mechanisms. This does not only refers to the textile, but in any physical model, these are different ways that we transport moisture, not only in textile. So I have taken seven ways or seven mechanisms which the moisture get transport. So it will be through wicking, it will be through absorption and adsorption, diffusion, evaporation, capillarity, permeation, as well as heat transfer. So any type of moisture transportation is governed through this mechanism. And some of them, say for example, wicking. It's a combination of capillarity, diffusion, as well as adsorption. So these are certain level of combination is also there, but we need to keep in mind any technological development that we do in the textile to manage the moisture from the textile, we have to look at these transportation mechanism. So just by looking at these moisture transportation mechanism, we will look at today what are the three pillars of moisture management techniques that are available for the industry. Right. So just for your reference purpose, let's have a very brief introduction or a very briefly let's look at what are these moisture transportation mechanism. It is because these terms need to be a little bit familiar and also it need to be understood very well for you to understand the technological development that has been done in the moisture management in textile. So if you take the term wicking, wicking basically refers to moisture transportation along a surface. This can be opposed to the gravitational force or else it could be through the transverse direction of the textile material, right? So therefore this wicking property is through the capillary action. Most of the time it is through the capillary action. Normally, if you take different material types, specifically the textile material, polyester and wool, they shows a very good wicking property compared to the cotton fiber. So we will have a look why. Why wool and polyester are termed as materials which has very good wicking property. And then if you look at this term absorption and adsorption, these are two terms. Sometimes you may have heard these absorption and adsorption. Absorption refers to uptake of the moisture into the fibers. So this is governed by the hydrophilic nature of the textile material, textile or any material. Cotton is a hydrophilic fabric, hydrophilic fiber. Polyester is not a hydrophilic fiber. So therefore the absorption looks at the hydrophilicity or it looks at the moisture uptake into the fiber. And then not in opposition actually, if you look at the adsorption, adsorption refers to molecules which comes and adhere on the surface of the fiber. It does not get into the fiber. So this is nothing to do with the hydrophilicity. This is the adsorption through certain physical forces. So I would rather say a polyester type of a fabric have a adsorption property, not absorption property. It just adhere to the fabric. It does not adsorb to the fabric. And then the diffusion. Diffusion involves transportation of the moisture at the molecular level. It is something different to the wicking, but wicking property of a material is also contributed by the diffusion. At the molecular level, through molecular forces, water molecule will transport from an area to another area. So this area basically refers to high concentration and low concentration of moisture. So diffusion will takes place when it comes to the sweat management in textile from your skin, where the sweat concentration is very high. And then if you take the outside of your fabric, so therefore the diffusion will take place at the molecular level of the fabric through molecular forces. So when it's come to the cotton, I will take always the example cotton and polyester because it's a little bit easy to understand. If you take the cotton, it of course absorbs the moisture, but because of the hydrophilic nature, because of the hydrophilic forces that it has, such as hydrogen bonding, it doesn't have a super level of molecular forces for the water to transport, water molecules to transport from one area to the other. So the diffusion of the moisture through a cotton fabric is not very good. But if you take the polyester, since it get only adhere to the surface of the material, moisture transportation at the molecular level through diffusion is very good in polyester material. And then there's something called evaporation. So the evaporation is to do with the macroclimate. If you can remember our thermophysio comfort model, we have the macroclimate. So for the macroclimate, when the moisture get transport and when it get to the outer surface of the fabric, it get evaporated through different forces. Maybe it get evaporated due to increase in temperature. Evaporation will take place, not permeation but evaporation. So the moisture evaporation is also important, and also you can improve the moisture evaporation through different mechanisms. Moisture evaporation is mostly effective when you have a thin layer of surface of moisture. That means the moisture which comes into contact with the air directly, it gets evaporated more faster. As long as you can spread your moisture evenly through a larger area, your moisture evaporation rates would be higher. So therefore, evaporation is also very important mechanism when it's come to the moisture management in textile. And then another moisture transportation mechanism is through the capillary. So these capillaries refers to very tiny spaces between the fibers. So because of these tiny spaces, what happens due to the surface tension, the moisture will get transport through we call it as the capillary action. It relies on the surface tension of the fluid as well as the surface tension of our textile material. And then another important mechanism for the moisture transportation is the permeation. Permeation is where we refer to small spaces, not through the capillary action, but small spaces, not through surface tension, but it will allow the water vapor to get away from inside of the fabric to the outside of the fabric. We call it as permeation. And the last but not the least, the heat transfer is also very important. Now you may wonder, heat transfer, and is it directly related with the moisture management? Although it is not directly related, but the heat transfer influences the moisture management to a greater degree. If you have a fabric that efficiently transfer the body heat, it has a very good heat conductivity, so then it can transfer the body heat efficiently. So such type of material has the capability to evaporate the moisture more efficiently. So therefore, the heat transfer property of the fabric is also very important when it comes to the moisture management. So all these 7 key moisture transportation mechanism, and having a very good sound knowledge about how does it happen, what is the physics behind them? How can you engineer the material to improve these mechanisms? Is very important if you are into developing a textile material with good moisture management property. So whenever you talk about any innovations in the industry gives which claims to have good moisture management properties, they have looked into these 7 moisture transportation mechanism, and they have tried their level best to improve those mechanisms. Right. So you can see 3 pillars here. I would rather call this as the 3 pillars. Technical aspect of moisture management. How do you improve the moisture management property? So the 3 pillars basically talks about, I have looked at the techniques available in the industry where they have utilized these methodologies to improve the moisture management, and we can basically categorize them into 3 pillars. That is, moisture management can be done through fabric structure and breathability. And the moisture management can be improved through moisture absorption capacity and the moisture transportation mechanism. So these are the 3 pillars that we are going to talk about. And then when we looked at taking some of the example from the industry and from the fabric available in the industry, according to which category they have looked at improving the moisture management property in the textile. So when it's come to the fabric structure and the breathability, this is a very interesting and an important pillar. So in this one, they utilize, so they uses different weave-on knit structures. Sometimes you may not think about it very important. You may not look at it as very important. But of course, not only in today's term, but in past also, they have looked at these different structures. But now in the textile industry, we do have weaving textile and knitted textile. And also you do have non-woven textile material. Specifically weaving, if I take an example, some of you may have heard about huckaback weave. These are specific weaves developed very long time back. Why have they developed these huckaback weave? Normally, hucksters refers to people who used to sell fabric, because now these days how do we buy fabric? We go to a shop and then we buy it, or else you online order it. But previously there are merchants who has their backpacks and then they bring the fabric to your doorstep and they sell it. So these hucksters have looked into specific structures because they need more comfortability, because they travel a lot. So the moisture management was something very important. So interestingly, they have developed certain woven structures where they have long floats on the woven structure. So therefore, the long floats mean the cover factor is very high. So these are technical terms that we used in different woven structures. The cover factor is very important because the cover factor basically regulates the moisture absorption level, the moisture transportation, as well as the heat conduction. So therefore, there are different woven structures that we can look into. So it utilizes different weave and also knit structures in order to enhance not only the breathability but also the moisture vapor transmission. Breathability is very important when it's come to the moisture vapor transportation. And then also these fabric structures under that pillar, we can look at different methodologies to develop microporous membranes and coatings. Not through only the structure, but also through certain after application of certain after finishes, you incorporate microporous membranes. So these microporous membranes act as wicking windows, and therefore they transport the moisture through these fabric structures. And then there could be certain coatings also. Sometimes there are coatings, when it get absorbed the moisture, certain hydrophilic functional groups get expanded, so therefore it will It will engineer the micropores. It will decide what the micropores should be once you absorb the moisture. So therefore, the fabric structure and breathability, engineering of the fabric structure and breathability through various methods of micropore generation is also used by the textile industry. And also, you need to look at the importance of the microclimate regulation for comfort when it's come to the fabric structure and the breathability. Because the fabric structure and the breathability, the moisture transportation, we need to do that in only one way. That is from inside your body to the outside of the macroclimate, not from the outside of the environment to the inside. It need to be a one way. So the one-way moisture transportation through the fabric structure and the breathability is very, very important. Right, so let's look at the second most important pillar. That is the moisture absorption capacity. So the moisture absorption capacity, in here I'm referring to the absorption, not the adsorption. So in this one, you can incorporate hydrophilic fibers or finishes, because we all know polyester doesn't have a very good moisture absorption capacity. But through incorporating of hydrophilic fibers, so that's maybe a reason why people blend cotton and polyesters together, because the polyester doesn't have the necessary moisture absorption capacity. When it's come to the moisture management, absorption of the moisture is very, very important. So therefore, you can sometimes blend the fibers, hydrophilic and hydrophobic fibers together, or else you can apply certain after finishes to increase the water absorption capacity. And in here, when it's come to the absorption, you need to balance the absorption as well as the dry. It's because we know cotton is a comfortable fabric. Cotton absorbs more moisture, but industries does not use cotton more frequently for active wear. Why is that? It is because although it has a good absorption capacity, it makes chemical bonding with the water molecule. Specifically, the hydrogen bonding is a very strong bonding. So therefore, when it's come to the evaporation, it does not get quickly evaporated. That is, we need to make a balance between the absorption and the quick evaporation. So therefore, sometimes the cotton fabric, the absorption capacities, they try to engineer it through the use of certain after finishes that the absorption level is a little bit lower. Cellulose acetate. When the cellulose OH group has been esterified with the acetate molecule, so then the hydrophilicity or making the hydrogen bonding with the water molecule can be controlled to a certain level. So therefore, people have looked at blending cellulose and cellulose acetate together, or else modifying the chemical structure of the cellulose in a way where the absorption capacity has been matched with the quick drying property of that material. And then if you look at the moisture transportation mechanism, yes, we have looked at 7 mechanisms. So in here, almost all the examples or the technical development that has been done, it talks about these mechanism and combination of these mechanism for the effective moisture management. So the capillary action and wicking properties is very important, and it is highly used technology or the mechanism, highly used mechanism when it's come to the moisture management. So this moisture transportation mechanism also looked at enhancing the surface energy to promote the moisture transfer. Enhancing the surface energy is very, very important. Now, if you take enhancing the moisture surface energy, so I will take a very basic example. Now, if you take the lotus leaf, the lotus leaf does not get wet. It just beads out the water droplets. Why is that? When it's come to the water, water tends to get into the form of a droplet. It is because they need to reduce the surface energy. So in order to reduce the surface energies of the water molecule, the best suited structure for the water molecules is to be in the droplet form. When it come and get contact with the surface, most of the time these water droplet get spread. Why is that? It is because the surface in touch with the water molecules, they do have high surface energies. So when it has high surface energies, the water molecules tends to get spread. Spreading is done through changes in the surface energy. So why the lotus leaf water beads? It is because it has already naturally engineered structure where the surface of the lotus leaf has comparatively lower surface energy compared with that of the water molecule. So therefore the water stays like in a bead. So therefore when it comes to the moisture management, you need to think about whether you want your fabric surface to be hydrophobic or hydrophilic. When it's come to the moisture management, we have already discussed, we need only a one-way moisture transportation. That is from your skin side to the macroclimate. So therefore, you don't need the moisture get diffused inside the fabric from the outside to the inside. So therefore, we can have engineered molecules inside the fabric, or we can have engineered coating structures of composite incorporated into the textile. When the moisture gets absorbed from the outside, it will get expand and form a barrier structure. So therefore, it will not allow, it will change the surface energy and it will not allow the water to diffuse inside, but it will get beads out away. And then you can look at certain coatings or certain structures. Once the water molecules get absorbed, it will lower the surface energy. Might be the pore structure will get contracted. So therefore, it will improve the surface energy to a level. It will lower the surface energy. It will increase the surface energy to a level where you can have the 100% wettability. 100% wettability means it is spread. The spreading area is very higher. If the spreading area is higher, that means the surface contact with the air and your surface is very high, so therefore the evaporation can happen faster. So therefore in surface energy enhancement or surface energy lowering is very important when you decide what is the level of achievement that you need in the moisture management. So in this pillar we will a little bit discuss about the importance of the moisture management in active wear and sports wear as well, right? So there were a few requests from me to get the permission to do the recording. Yes, we will record this session and we can share it with you all. Okay. Okay. Now the fabric structure and the breathability. If you try to imagine that through this image, this is how it looks like. You have the fabric where you have your body, where it regulates the body heat, and then you have the skin. And then through the skin, you basically sweat. And then you have the microclimate. So if there's anyone who cannot imagine what a microclimate means, this is your skin. Let me have my pointer. You have your skin, and then you have your fabric. Between the skin and the fabric, this is micro. Like sometimes it's this microclimate, the space is very, very small. This is a zoom version. Okay. And then the fabric. So then the moisture will get from the through your skin to the microclimate, to the fabric, and then to the macroclimate through different mechanisms. It could be adsorption. It will get absorbed and then it will get wet and then it will go out from the macro to the macroclimate through evaporation. And it could be through diffusion. And then for all these things, whether it is adsorption, whether it is diffusion, whether it is wicking, not only the fabric property important, not only the fabric property, but also the condition in the macroclimate is also very, very important. It is because all these moisture transportation is governed and it is catalyzed by the climate condition through heat convection, heat radiation, and the airflow, wind speed. So that is why we have discussed about that thermophysio comfort model. All right. So the moisture vapor transfer is governed by the interyarn and interfiber space. You have yarns. Inside the yarns, you have fibers because yarns are made out of fibers. So therefore, the moisture vapor transmitters. In here, not the moisture droplets, but the moisture vapor transfer is basically governed by between the yarns, how you interact with the moisture. And then the interfiber space is also important. So sometimes you may have heard about microdenier fibers, very small fibers compared to the macrofibers. Why people have looked into microdenier fibers? Because you can have yarns done from microdenier, very tiny fibers. Why tiny fibers performs well in moisture vapor transfer? In the moisture transportation mechanism, why microdenier fibers performs very well? It is because we talk about increase in the surface area to volume ratio. Because of the increase in the surface area, be uh, it will be more exposed to the surface. If it has more surface area, it will be more exposed to the external environment. So then the evaporation rates are higher. Right? So likewise, there are many things, but for the moment, just we have to keep in mind interfiber spacing and inter-yarn spacing is very important when it's come to the moisture vapor transfer from your skin to the external environment. And diffusion of the water vapor through the airspace between the fiber is also contributing highly for the effective moisture management. Not only the diffusion, but also the absorption and the transmission through different mechanism, maybe the capillary action, maybe the wicking, as well as the desorption is also important. Desorption means once it's been absorbed, how fast it can get desorbed. It depends on the molecular forces that you have. The desorption rates will depend on the surface area, how well your moisture is spread. So then every layer of the moisture can get a direct contact with the air. So therefore it can get evaporated faster. And then the transmission of the water vapor by force convection. Convectional forces are very important because the convectional forces create a concentration gradient between the fabric, between your skin as well as between your macroclimate. So therefore, this gradient creation through convection or radiation is very important because it allows you for the first convection and the post convection allow more moisture evaporation rates. Right. So let's take one by one these pillars and start looking at what are the technical development that has been done and how you can approach achieving high level of moisture management in textile for the comfortability of the wearer, because that's the ultimate goal. Because we all, some of us are in the research area, some of us are in the industry area, some of us are looking at technical textiles, high performance textiles, and the comfortability of the wearer is very important when it's come to marketing of the textile. Right. So let's look at utilizing different weave and knit structures. Now, when it's come to the weave and knit structures, there are technical factors that we need to consider. Now, fabric structure and breathability is important because of these three things. It is because the fabric structure and the breathability governs the diffusion of the water vapor through the airspace, and also absorption, transmission, and desorption of the water vapor by the fibers, and also the transmission of water vapor by the force convection. Actually, we are looking at three different technical developments in these three areas. Now, in here, you can see one equation and one experimental setup, right? So this is a manometer, the specimen airflow meter. In here, actually, you can physically test your sample, and then this is a testing setup that you can test physically the air permeability of your textile material. This is in practical terms how you test it. But in theoretical terms, there are different equations which combines different technical parameters of the textile and decide the air permeability. So this model development is very important, which we never look at. Normally in industries, in universities or in research institute, most of them look at material development directly. But it is important before we go for the material development, certain theoretical model. You substitute certain amounts, technical details into these equations, and you do certain model development, and then you come up with a theoretical model. Okay, if I produce this type of a fabric, it will have this level of air permeability. So these can be done in the factory level. Sometimes we can employ or we can have maybe certain researchers, certain students, or certain, I don't know, individuals who will look into developing these models theoretically. But in the sense, when they develop a theoretical model, they need to test it against the physical testing. So anybody who has the capability of thinking a little bit, learning a little bit about technical parameters which contributes towards the air permeability, maybe the weave structure, the thread density, the thread count, and the weave structure, the cover factor, the flexibility, the woven fabric structure, the twill angle. If there's someone who can look into different of these parameters, try to get different fabric from these parameters, and then he or she can check the do a physical testing and do the air permeability testing. And then you can have develop a theoretical model where you have the theories developed and then tested, and you have a model. So whenever you substitute parameters, then you know this is the air permeability. This is one of the areas that the industries actually need. It because we get different types of fabric to the industry. But the thing is, they claim technically they do have these types of performance. But then there's another batch coming, and sometimes according to the testing, the fabric doesn't perform according to the level of expectation. So then we look into what are the possible failures of this fabric. But if there's a model that has been developed which bridge the theoretical aspect and the actual performance, we can tell because of these parameter changes, this fabric does not perform. And then even in the technical level, we can look into outsourcing different level of yarns, different types of fibers, different types of woven structures, different types of knitted structures. And just by telling our supplier, okay, provide me with this type of a yarn, having these types of material properties, having these types of fiber thickness, and then let me have a fabric structure of this nature. It is because I know then if I get a fabric of that quality, I can achieve this level of air permeability. So that is the importance of getting into models. This is something that we can look into in the textile industry. All right. So in here, I have taken another example. This technology calls the microdenier technology. So this is available. You may all know this is available. Industry එකේ ඉන්න අය ගොඩක් දන්නවා ඇති මේ විදිහව තියෙනවා. So we call this as a soft touch. I think this is the name that's being used in the industry. So they are looking at absorption, transmission, and desorption. Absorption, transmission maximize, desorption maximize. Through what? Through specific fibers. They have not changed the material, but they have changed some physical aspect of the fiber. That is the density, linear density, denier. denier count of the fiber. So this is under the scanning electron microscope. How does these two looks like the cross section? A normal polyester and a microdenier fiber. So if you look at the cross section in a model view, this is how the microdenier fiber looks like. It's because more even, more compact. The surface area is high. See, the surface area is high. So therefore, high density woven fabric, we call these as high density woven fabric or microdenier fiber developments. So the fabrics made using these types of very tiny or microdenier man-made filaments have a very good breathability. It is because they have a very densely packed structure. It's very thin and it is also very smooth. Therefore, it has high surface area. Therefore, because of the high surface area and because of the very tiny spaces, it has a very good water vapor permeation. Water vapor can be transmitted through the fabric because it has very small or tiny spaces in between. And also, these microfibers do not swell. There are certain fibers, such as viscose rayon. When it absorbs the moisture, it gets swelled. There's a slight swelling in all types of fibers. When the moisture get in, it tend to swell a little bit. But the microfibers does not have that capability of swelling. So therefore, they are the best suited for these types of purposes. Microfibers do not swell when wet. High density fabric made out of microfilament yarn fabric exhibit very, very small pores. Small pores means evaporation. Moisture vapor evaporation is good, but moisture droplet absorption will be comparably lesser because they are compact. Because of the tiny structures inside, when they combine with each other, there will be very tiny gaps between the fibers, interfiber area. So the capillary action will also be higher. So therefore, not by looking at high dense coatings, not by looking at high dense packing material, not by looking at co and sheath material, you can look for technologies where you incorporate microfibers as microdenier technology, and then you can look at improving the absorption, moisture transmission, as well as the desorption or the moisture vapor, moisture evaporation when the moisture come into contact with the air. Okay, so this is a technology, one example. There could be many examples. I'm not taking all the example, but I'm giving you the essence of these technologies. These are the ways that you can look into when it's come to the moisture management through this fabric structure and breathability section. So by now, you know, there are three pillars. Three pillars talks about three different things. So therefore we can have three different level of technological development, right? And also this is another area. It is through the structure, absorption, transmission, and desorption of the structure. So if you can have yarns, this is a huckerback view. It is a little bit different to a plain woven structure, and also the Royal Oxford view. In here, you all can see the thing which I have told you, these floats. Because of the floats, they can basically compact very well. And also, if you have done these fabrics with the yarns having microdenier fibers, you all can see the area that it can cover because of the floats, they are higher. Make a plane. Now, if this is a plane view, like one up, one down plane view, the floats are not here. So the floatings are here means the cover factor is very high. So this is how they have used the advantage of the cover factor of the woven fabric with the floats, and then they have tried to improve the hydrophilicity. So therefore, the absorption, transmission, and the desorption of the water vapor by the fibers are maximized. So these are very little technologies that people never look into. Most of the time, we never look into the structure, but we talk about technical textile, high performance textile by having high level of fibers, technical fibers. But this is an area, very important area, where you look at the fabric structure and breathability through different woven or knitted structure. Right. So this one, various methods of generating micropore membranes and the coating. So these micropore membrane, now when it's come to the fabrics, if your supplier has already supplied you with a fabric, we have very little space to do any modification at the yarn or the fiber level or the construction level. Only thing that we can do is we can look into developing coatings. So I can remember when we did research, one of the drawbacks that we had was in the textile industry, most of the time, for it to be more production feasible, we looked at coatings. This because it's very easy to apply. You do have different setup in the industry where you can apply the coatings. So in here we look at having applied different coatings which basically repels the liquid water, but it will allow the water vapor permeation through the gaps between the fibers. So the moisture vapor permeation and the waterproof coated fabric can be done by application of different membranes. Microporous membranes can be applied. You can apply a coating and you do certain curing and then you can achieve microporous in the membrane. So these microporous membrane, they have holes which are very small, somewhere around 2 to 3 micrometers. And also you can have raindrop which is having the smallest size 100 micrometers. So then what can happen? What can happen? Because of the holes which are less than 2 to 3 micrometer, it will not allow the raindrop to come in. And also they are very much larger than a water vapor molecule, which is around 40. So in here, pardon me, these holes can be in between 400 micrometer to 100 micrometer to 40 micrometer, right? So this is a very simple technology again. You produce porous membrane where the pore structure is capable of allowing the moisture vapor to evaporate, but the rain droplets does not comes in. So sometimes this membrane or the materials can be developed using different techniques. There are different technologies developed and there was one application in Japan. They have this rice husk as one of their major waste because this is a rice eating country. The staple food is rice. I think in Japan the staple food is rice. I don't know. They eat rice a lot, like in Sri Lanka. So therefore rice husk is a problem. Although you use rice husk for different purposes, still it's a problem. So therefore Japanese has looked at this rice husk and it has a very interesting structure. When you subject the rice husk to certain mechanical and thermal treatment, it can produce triporous structures. We call it as triporous structures. That is, you have nano, micro, and macroporous. Why do we have nano, macro, and microporous? It is because it can absorb different level of moisture. In there, they have used that one for application of water purification by application it into a textile. But of course, such type of porous membranes can be incorporated for effective moisture management as well. Because in there, you looked into vapor through nano and microporous, but blocking the droplets of the water from the outside, that is outside to inside, you block the water, but you allow the moisture to transport from your skin side to the external environment. And this is another development that was done to enhance the water vapor permeation through moisture regulating microcapsules. This been reported in research articles. So they have a composite with a polyurethane coating on a leather material. And the beauty of this polyurethane coating is this polyurethane coating comprises of moisture regulating microcapsules. So therefore, when you absorb the moisture, it gets swell. When you desorb the moisture, it gets contracted. So once the moisture gets desorbed, it will allow more moisture wicking through the capillary action. When it absorbs the moisture, it will block the moisture penetration from the outside of the fabric to the inside of the fabric. So this is a technology developed to enhance the water vapor permeation, and we can look into different application if you use this technology. Right. And then the second pillar, the moisture capacity improvement. So the moisture absorption, perspiration and quick drying is something to do with the moisture absorption capacity. Moisture absorption capacity basically looks into hygroscopic and the hydrophobic nature of the material. So there are theories that was developed. In here, in the table, it was given if it is a hygroscopic, then water absorption, drip diffusion, and co-suction height, because these are some of the performance parameters that we do check for the moisture management. And when it's come to the quick drying technologies, that is the evaporation rates are very high. So therefore, we need to look into specifically the evaporation rate and the water moisture permeation rates. So therefore, moisture absorption capacity improvement can be done by looking at these specific properties itself. Not just that you improve the moisture absorption capacity, but if it is a hygroscopic or a high moisture absorption capacity material, then the absorption percentage as well as the drip diffusion and then the co-suction heights or the wicking amount is very, very important. Wicking performance is very important. So this is the level of achievement that we already have in these types of research area. And then incorporating hydrophilic fibers as well as finishes. You can apply finishes also, because at the fiber or the yarn level or the structure level, it's already done and finished. You can't do any modification, but you can incorporate hydrophilic fibers. And when you incorporate hydrophilic fibers, you need to maintain a balance between the absorption as well as the quick dry. Otherwise, it will not perform well in the moisture management. Say, for an example, they have looked at cotton, bamboo, lyocell. Lyocell is a modification of the cotton and it has a very good moisture management property compared to the cotton, although it has both the cellulose. The bamboo also, it has a certain level of cellulose, but the bamboo has a very good quick drying property. Although the cotton does not have a very good quick drying property, but it has a very good moisture absorption capacity. So therefore, we can look into different material combinations and then we can optimize or we can maintain the balance between the moisture absorption capacity as well as the quick drying performance. And this is one of the very important area and many research has been done in this third pillar. That is the moisture transportation mechanism. So if you look into capillary action and wicking properties, so these are different development that they have done. So they have developed structures which block the microchannels at a certain location. So therefore it will lower the fabric absorption capacity from the outside. So therefore the original water spread without channeling or blocking. Therefore, it will enhance the spread with the channel blocking. It will enhance the water spreading with the channel blocking. So therefore, it can get evaporated faster. So these microchannels have been forced to spread the given water over a large area as long as you can increase the area of contact with the air. So then the evaporation rates will be higher. So in here, you all can see the moisture wicking is on and the spreading is happening in all radial directions. So that means it's been engineered it's been engineered in the capillary action as well as in the wicking property. So therefore, this is a very well moisture management technique that we can utilize. And then this is another technology that we can think about when it's come to the improving the moisture management through moisture transportation mechanism. That is wicking window technology. So in here they have applied an application of a coating through a print and it has a very high performance in the wicking. And also in here, if we apply this print on the skin side, the perspiration or the sweat will get wicked through these wicking windows to the evaporation area. So therefore, this wicked moisture will get evaporate faster. So this is a common technology that they normally use in order to improve the moisture management property through the capillary and the wicking action. And this is the same. Through this, actually, they have developed the technical backside of the fabric. It's very more or less not visible. The wet patch is not visible. Why? It is because all the moisture has been transported to the outside of the material. So it has more water content at the front side of the fabric. It has lesser water content in the back side of the fabric. And once it get to the front side, it has these capillary actions and the wicking property for it to spread into a very high radial area. So therefore, it will evaporate faster. And also, there are no spots of water loving and water hating areas at the front. It's uniform. It's very, very uniform. It's because sometimes when you blend the fibers together to have polyester and cotton blends, you will see there are spots. Spots pain, it's visible to the naked eye. It is because they are not uniformly spread. Water loving and water hating area, if they are not uniformly spread, you will see spots. So therefore, if the radial spreading is very high, you can evaporate them more quickly. Right. So in this one, you talk about hydrofunctional polymer groups. You incorporate specific hydrofunctional polymer groups. What does these hydrofunctional polymer groups do? They respond to changes in the body temperature, not to the moisture. That's the important thing. You think hydrofunctional means it will respond to the moisture. No. These specific applications, they look for hydrofunctional groups that respond to changes in the body temperature. So therefore, when it's come to that body temperature, it provides a cooling sensation. Specifically, if our body temperature, the core body temperature goes beyond 28 centigrade, these fibers start activating. At this temperature, the structure of the polymer changes. Structure of the polymer changes due to the thermal response. And then it increases the fabric ability to wick more moisture. So that is a technology by selecting a specific polymer molecule or making it into a fiber, right? So this technology is capable of reducing the wearer's core body temperature by maybe 1.5 to 2.5 centigrade. That's the most allowable limit. Okay. So this is a technology that they have looked at capillary action and wicking improvement. Although we never think hydrofunctional polymers, whether it can be utilized for such application. And also, this is a close-up look of a 4-channel Cool Max fabric. We talk about trilobal fibers. Why? It is because it creates these channels. These channels act as capillary channels. And these channels basically speeds the moisture to the outer surface. It has more moisture wicking property. So therefore, the effective moisture management of the fabric can be achieved. And then enhancing the surface energy to promote the moisture transfer is also very important because we have discussed if the surface energy is very high, your surface will become hydrophobic. If you have a surface energy very low, that means your surface become more hydrophilic. Decrease in the contact angle basically tune the wettability of the fabric. So a surface with a lower surface energy will cause poor wetting, and application of very functional finishes into the textile allow more moisture spreading. Sometimes you can see water spots. If you can see the water spot, that means you have areas of water loving and water hating areas. So in such cases, we can apply functional finishes which can spread the moisture. Sometimes in structurally you improve it, but of course, you may need functional finishes as well. Functional finishes that will enhance the moisture spreading. And also the moisture transportation, the surface energy enhancement or engineering the surface energy can be through Janu structures. We call them as Janu structures. In a fiber, normally it is uniform, right? Normally in a fiber, if you look at the cross section, this is uniform. But in this application, they have looked into not actually a sandwich structure. Half of the material is different. Side A and side B is different. So through this Janus application, you can engineer the surface energy because it has different physical and chemical properties. So therefore, if it has different surface energies in the two sides, it allows moisture to be absorbed and then wick into a specific area. So these Janus fibers are also engineered fibers like in here in order to improve the capillary action and the wicking action through surface energy enhancement. All right. So this is actually an example which was published in a highly impact journal where Janus structures with dual discrepancies in the surface energy as well as the fabric porosity results improved water transportation through capillary and wicking action, right? In here they have used a certain level of a polymer where they look into these types of Janus structure of the fiber, and then once they are being incorporated into the textile material, they have shown a superior moisture management property. All right. And then transmission of the water vapor by forced convection is also very important. It is because the moisture is taken up from the fiber by the flowing air of the macroclimate. So this is, we call it as the forced convection model. And the forced convection model is very important when we look into the enhancement of the moisture management property. So the mass transfer of the moisture will be guided by exciting differential moisture concentration in different sides of the fabric. So then from the high concentrated area to the low concentrated area, moisture will get effectively transported through this forced convection method. And then last but not the least, I will not go into details, but any moisture management textile or MMT textile, they need to be tested for its performance. So when it's come to the performance testing, these are some of the testing that we can do. Water vapor permeation, total absorption capacity, rate of absorption, surface wettability, contact angle, vertical wicking, spreading, transverse liquid spread. All those are certain level of testings that we can do, or say a list of testing that we can do in order to assess the moisture management property of the textile that we have developed. So with that note, I suppose you all have got something from this discussion. The discussion is open for question and answers as well. You all can discuss with us maybe your experience also, what you all have seen in the industry, and from the discussion points, if you need further clarification, if you have some questions, we can answer also. Thank you.
Thank you, Dr. Nadika, for the wonderful delivery. So as suggested, now if there are any questions, so you can raise your hand. So let me moderate, and I can can ask that question direct from Dr. Nadika. Or else you can also, if you want, you can type into the chat box and I can refer that to Dr. Nadika as well. So let's take this as a collaborative effort, and if you want to share something also, let's take this opportunity to do that.
Yeah.
Hi, Nanatunga. Yes, so you can go ahead, please.
Yeah, Mr. Ruchira Jesena, I'm very much thankful for the opportunity given for me to raise the hand and ask a question. I have one question regarding the thing that Dr. Nadika explained at the beginning of her presentation. As far as I understood, she explained about the importance of the surface energy. There she told like the more the surface, or the higher the surface energy, water molecule will be attracted to the surface of a textile. And then again, I have this question, like, I'm not very much clear about this thing. Like she said, like after the transmission of vapor or water molecule from the inside to the outside, then it should be like properly spread to cater to get it evaporated by the wind or the outside forces. Can you kindly elaborate on this a little bit?
Yes, thank you very much, Ranatunga. Yes, you are requesting for a clarification. The surface energy basically refers to the surface wettable property, wettability. So it's something to do with the like the wicking and the capillary action is governed through fiber. Actually, the interaction between the interfiber and the inter-yarn interactions. So in here, when the surface, when I refers to the surface energy, now we have looked at these Janus fibers. Now, in the Janus fibers, there are differences in the fiber itself. They have created differences in the surface energy. That means the surface wettability. If you have one side of the fiber which does not love water, but if you have another area of the fiber which love the water, and if you have a gradient of hydrophobicity and philicity through changing the surface energy, it will basically create a force for the molecules to get transport from the water non-loving area to the water loving area. Okay. And then in the water loving area, if you have developed certain structural effect for the evaporation to take place quickly, so therefore, it will get evaporated quickly. So now this moisture transportation can happen through different mechanisms. You can have the capillary action. Capillary action means due to the surface tension, the water molecules get transport from one area to the other, high concentrated area to the low concentrated area. And then there's the wicking. Wicking basically works with different models. That is at the molecular level, at the diffusion, the capillary, all this contributes to the wicking. And also you can look at the surface energy as well. Surface energy, by creating a gradient in the surface energy across the fabric thickness, you allow the moisture to transport from high concentrated area to the low concentrated area. And if you request how does the evaporation takes place when it's come to the low concentrated area, then you can look for specific application where the water get evaporated more effectively through spreading. You allow more spreading, and then through the spreading, you allow more contact points with the air. So therefore, the evaporation is optimized. So that is what the surface energy refers to. All these factors are interconnected. The mechanism now this moisture management, the way that we improve the moisture management can happen through different mechanisms by incorporating different physical models. If I explain it correctly.
Okay, thank you very much, Dr. Nadi.
Yeah, thanks, Ranatunga, for the question also. Are there any other questions, any clarification that you would like to raise to Dr. Nadi? Hi, Mihri. You can ask. Please go ahead.
Hi, Dr. Nadika. Thank you so much for the presentation. It's a really nice presentation. I just wanted to ask the slide that you explained about the fabric space, like 40 micrometer, and the rain droplets is 100 micrometer.
Yeah, my fault. There was a typing mismatch in that one. I think you are referring to this one, right?
Yeah, that one, yeah. So you said that the water droplets won't transfer through the fabric to the side of the body because the because the rain droplet will be like 100 micrometers.
Yes.
But is the fabric itself super hydrophobic?
Normally, the hydrophobicity is achieved through the selection of your material. Normally, even the polyester, although it doesn't have any water-loving molecules, but it is not hydrophobic. Hydrophobic in the sense we refers to the contact angle of the water droplet with the surface. So if it is hydrophobic, normally it refers to a contact angle more than 90 degrees. And if it is super hydrophobic, it is something more than 150 degrees. So therefore, the textile materials itself, we cannot, just from the instinct material property, they don't have a hydrophobic such level of hydrophobicity we don't have. But you can enhance the surface energy and then achieve the contact angle if you want it less than 90 degree for it to be more wettable and hygroscopic. Then there are different hydrophilic coatings that we can apply. And if you want to enhance the surface energy to a level where you talk about a hydrophobic fabric, where you talk about super hydrophobicity, still you can have certain structural changes as well as molecular changes through certain applications of the coating. So then you achieve that level of hydrophobicity. But also in here, I'm referring to in this slide, moisture evaporation or moisture permeation through porous membranes. It is because if you have a porous somewhere less than 100 micrometer, normally the maximum droplet size of a water is measured to be 100 micrometer. So if you have a pore less than 100 micrometer, that water will not get permeate through that membrane. It because the water droplet can't permeate through that. But if you have a pore membrane which is having less than 100 micrometer, but if it is more than a 40 micrometer, which is the size of a water vapor, then it will allow the water permeation. Water drop, not the water droplet, but the water vapor can be, we call that as permeation. It can get transport through the pores. We call it as the permeation. So the permeation allows the water vapor to go out, but it does not allow water droplets to come in. So that is through incorporation of porous membranes. You engineer the porosity of the membrane, which will not allow the droplets to come in, but it will allow the vapor to transport. So this can be done through fabric structures as well. You have a fiber, you have a coating on that one, where the coatings has already increased the surface energy of the fiber in the yarn level. So therefore, it will basically beads away the water droplet. But you will have a construction, according to the fabric construction, you do have yarn gaps, you do have fiber gaps, very small. So therefore, any sweat which get evaporated through forced convections, it will get evaporated through those pores. But the water droplets will not come in. It will get bead away. That is in here what we are referring to. Various methods generating micropores. Micropores can be generated by application of different membranes or separate membranes, but also you can have it a yarn level application, a coating where you look for hydrophobicity, but then you have constructed the structure where the water vapor can get permeate away through the pore structure.
Okay, thank you so much. You explained it really good. Thank you.
Thank you. I think, Dr. Richard, I have got few messages from Yasit. Where does the nylon stands compared to cotton and PET in the terms of ml? So compared with the cotton, I would rather say it's not a hydrophilic fiber as such of cotton, but it is not a hydrophobic or water non-loving. It doesn't have, it's not a hydrophobic structure, chemically hydrophobic like in polyester, because we talk about amine groups in there. Nylon and wool both, they have amine groups. Amine group can make hydrogen bonding with the water molecule. But when you compare the amount of amine group in there chemically in a molecular structure compared to the hydroxyl groups in a cellulose molecule, number of amine groups are comparably lesser. So therefore, I would rather say, now if I rank the nylon, cotton and polyester, cotton has a higher level of water absorption capacity because it has more hydrophilic or water-loving molecules. Nylon is in between, not up to the level of cotton, but it's not like polyester because polyester, it has an ester group. Ester group cannot make any chemical bonding with the water molecule. So therefore, it has a very, very low level of moisture absorption capacity. So therefore, to answer the Yasit question, nylon stands in between cotton and polyester. Right. Have I answered your question, Yasit?
Yes, Dr. Nadika, thank you.
Okay, thank you. And there is another, actually not a question, request. Missed the initial part of the session. Is there a way to get the recording? I think yes, we will be
yeah,
sharing.
Dr. Adhika. So yeah, that's what I said. I mean, if you register the newsletter, so we'll be uploading this to the internet, and the link will be shared. So
Okay.
you can later also you can access this and go through.
There's
And
another question.
yeah. So I have many. So you can go ahead, please.
Yes.
It's from
Thank you, Dr. Nadika, for the lecture. Can you give some commercial applications like these moisture management applications are being used maybe with Nike, Adidas or so
Yeah,
that we can refer later?
yeah. I have come across with specific after finishes provider Hikey. Hikey is one of the companies which provides after finishes to the textile industry, and they claim to have these functional hydrophilic polymers which respond to thermal, which I have described in the lecture in the discussion. So Hike is one of them, and also Nike and Adidas. I think they refers to some of these technologies like Cool Max, Climate. There are like if you take a report actually in the industry, they do have the access to these different reports. There are many plethora of materials developed in the moisture management which used in the commercial scale.
Okay, thank you very much.
Okay, I may go to this question. Does high surface energy materials support the already transmitted water vapor on its surface to evaporate? Or should we allow these water drops spread evenly by again making the surface feely? So hydrophobicity and the felicity with the surface energy refers something about the absorption capacity. The evaporation actually refers to the molecular level interaction of the material with the water molecule. So therefore, once it's been get into the outside of the fabric, the spreading and the wicking, it will be managed by other mechanism, capillary action, diffusion forces at the molecular level. And the evaporation basically refers to the evaporative level of the material. If it is getting chemically bonded with the material, so that means it will not allow the moisture to get evaporated. So high surface energy materials, basically they look into hydrophobic nature of the material. So therefore, it will not have any moisture chemically bonding with the moisture or the water molecule. So then it will allow more moisture evaporation. If I answer your question, Ranatunga, HANS.
Yes, thank you very much again, Dr. Nadika.
And there's another question, how to get registered for the newsletter. Can you please send the link here?
Yeah, so let me share it again. So the link is given. It's a Google form. Just fill out your information, just your name and the email. So the emails are not publicly shared. So these are within our database. They are not public share. So we'll send the emails or the relevant notices directly to you. So they are not visible to anybody else. Yeah? So I share this now. So you can click on the link in the chat box that are given in the chat. So you can go into that and register. Yeah. Yeah. So with that, then so let us thank Dr. Nadika for the wonderful presentation and following Q&A session. And also thank you very much for participating to this the session number 2 of Fiber Focus webinar series. And we'll be continuing this series in the future as well, trying to discuss usually some of the topics that are not really discussed in this detail. Okay, so we want to delve into these concepts and perhaps dig deeper so that you can actually have a utility you can take out, especially when you develop your materials, when you select your materials, and also when you work with these materials, you will see much more broader overview on how we work with them. So we invite you to connect with us in the future sessions also. With that note, I thank all of you for the participation. Thank you very much.
Yeah, thank you everyone for the participation. Thanks a lot. Your presence means a lot to us because we think there's someone who can take maybe the information that we do have, and we would like to share all those information with the industry, and we hope your effective participation for the upcoming webinars as well. And also thanks a lot for Dr. Ruchira for organizing this webinar series. Thank you all.
Okay, thanks. See you guys.